Okay, this lesson is on the vector equation of a line in 2 dimensions. So we're learning to find vector, parametric, and symmetric equations of a line in 2 space. So we're going to consider a line in a different way than we did in grade 9, 10, and 11. Consider a line that passes through the point A, negative 1, 4. So we know our line goes through this point, negative 1, 4. And has the same direction as the vector m equals 3, 2. So we call this the direction vector. And that vector we know would start at 0, 0 and end at 3, 2. So this would be our direction vector. So this is our direction vector m. And if a line goes through this point but has this direction vector, it's saying that it's parallel to this vector. So it's similar to a slope in that if we want more points on the line, or we want the point to have this slope or direction, then from this point we know we would go over 3 to the right and up 2, over 3 to the right and up 2, which doesn't fit, so we could reverse it like that. And then we can draw in this line. So this is a line parallel to a direction vector, but a line has arrows on both ends as it goes on forever in both directions. So here's our line. And this is our line with this point A here at negative 1, 4, and has that direction m3, 2. So we sketched it. So now it asks us to determine the equation of the line we drew in first slope-intercept form, so back to grade 9. So given a direction vector of 3, 2, we can convert that to a slope. So if the direction is 3, 2, we know the slope is rise over run, so in our case it's positive, so it's 2/3. And we also know a point on the line is a, negative 1, and 4. So we know our slope and a point, we can use y equals mx plus b to find the value of b. So 4 equals 2/3 times negative 1 plus b. Add 2/3 to both sides to get b by itself. Oops. You need a common denominator to add fractions. So we'll make that 12/3 plus 2/3, or b is 14/3. Which is 4 and 2/3. Make sure that looks right here. So if we're looking for our y-intercept, 1, 2, 3, 4, and 2/3 makes sense. So the equation of our line in slope-intercept form would be y equals 2/3 x plus 14/3. Standard form, also called scalar form, which we're going to learn about soon, is the form ax plus by plus c equals 0, where a, this coefficient, has to be a positive whole number. So we have to use algebra to make sure it's positive and a whole number. So we're starting with y equals 2/3 x plus 14/3. So I'm looking for the number in front of x, so the coefficient. It's a fraction, it's positive though, so in order to eliminate that fraction, we're going to multiply every single term by the common denominator, which is 3. So that would give us 3y equals 2x plus 14. And then we want to put it in this format, so I'm going to subtract 3y on both sides and organize it so I have my x term first, so 2x minus 3y plus 14. And then, so therefore in scalar form or standard form, our equation would be 2x minus 3y plus 14 equals 0. Okay, so those are both forms we've looked at in grade 9 and 10. Vector form is new for us. Okay, so we're looking at this line again, and we want a vector equation of the line. So a vector equation of the line, we use r vector, okay, which is a vector, okay, is equal to, so we start off with the position vector of a point on the line. So thinking that we're going to use the vector from 0, 0 to negative 1, 4. So in this case, if we call this the origin O, then this vector from the origin to a point we know on the line could be thought of as vector OA. Okay. And then this represents a vector from 0, 0 to any point on the line. So in other words, this is the position vector of any point on the line. So the vector from 0, 0 to any of these points along the line, which there's an infinite number of. And then you can consider, that's the left side. On the right side, that's how you're going to get to all of those points. So to get to all of those points, we're going to do a vector sum. So we're going to do the vector from O to A, and then from A to some point we don't know. I'll call it a point P. And point P can be anywhere. I'm going to put it somewhere, and that point P is going to be point PXY. Okay. And if I add them tip to tail, so here's OA plus AP. So this pink vector here is vector AP. Okay, so vector OA plus vector A to P. Then the resultant of that is going to be R, which is our vector from 0, 0 to any point PXY on the line. So I'll draw in that resultant in red here. Or no, maybe I'll use a dark green color to stand out. So from 0, 0 to any point P, and that point P can be moved anywhere, but this vector equation will always stand. So this vector here is OP, which is also the vector R, okay? All right, so OP is, no matter where we move the point along the line, could always be found by going from O to A and then adding on A to P along the line, okay? So it will just matter how long this vector AP is and whether it's going upwards and to the right or downwards and to the left, okay? But that will always hold true no matter what point on the line we're talking about. So if we move back down here, R again is this vector from O to P, and we know O has the coordinates 0, 0, and P has the coordinates x, y. So if we find vector OP by subtracting P minus O, then we would get vector R as x comma y. Okay, so the position vector of any point on the line is equal to O to A. So if we do A minus O, we're going to get negative 1, 4. Plus, so this one is the kind of trickiest one because remember it can change. So it depends on where A to P is, okay? So we could do our subtraction and say it's going to be x minus negative 1, y minus 4, which is true, okay? But what I want us to think of this vector A to P as is it's a scalar multiple. It's parallel to this vector M that we know, and it's a scalar multiple of it. So we would either be, in this case, it looks like it's shorter than vector M, or if P is like way up here, it's going to be longer than vector M, but it's going to be some constant times this vector M, or if it's down here, it's going to be a negative constant times that vector M. So I want us to think of this vector A to P as some multiple of vector M. So we're going to use T as our scalar. So this is a scalar or a number, times vector m, because we know it has that direction. And then we can just fill this in. So t, some number, some constant, some scalar, times vector m, which we know in this case is 3, 2. Okay, so that's kind of what the vector equation would look like, but you'll see in the way we'll write it, we know r is xy, so we'll always say r. That denotes a line for us. So the vector equation of the line is r equals -1, 4, which is the position vector of a known point on the line, plus t, so some constant, times the direction vector, 3, 2. And that is our vector equation of a line, where t can be any real number. And we call t a parameter. It can take on any real value, and that will make this part our AP part, which we said can be bigger or smaller or in the negative direction, depending on where the point P is on the line that we're trying to find at that given value of the parameter T. Okay, so that's called the vector equation of a line, a different way to look at a line. So definition, a position vector is the vector joining the origin to any point Pxy. We talked about that. Any point on a line can be thought of as the vector sum of the position vector of a known point on the line, O to A, and a scalar multiple of the direction vector, T times the direction vector M, where T can be any real number. All these points together form a line. The vector equation of a line passing through the point A, A1, A2 with a direction vector M equals M1, M2 is defined to be R equals A1, A2. Again, this is a position vector of a point on the line. Position vector of known point on line. And M1, M2 is called the direction vector of the line. And T can take on any real number, and it's called a parameter. So note, vector R is also xy. It's the position vector of any point on the line. So use the vector equation of the line in example 1 to determine the coordinates of 3 more points on the line. So here's our vector equation of the line that we drew. And if we want to find 3 more points on the line, all we have to do is set t equal to a value. So we can let t, it can be any real number. So I usually use really easy values. So if I let t equal 1, then to find the position vector of another point on the line, I would say r is equal to -1, 4 plus, so 1 times 3, 2 is just 3, 2, and then add those vectors together, and I would get -1 plus 3 is 2, 4 plus 2 is 6. So that means that 2, 6 is a point on the line. And that's as easy as it is to find a point on a line. So let's just look back at our picture here and see if 2, 6 is in fact a point on the line. So 2, 1, 2, 3, 4, 5, 6, yes, it's a point on the line. Okay, we could also let t equal -1. And we would get r equals -1, 4. So if we let t equal -1, that would be multiplying each of these by -1. So plus -3, -2. And we would get r equals -1 plus -3 is -4. 4 plus -2 is 2. And that should mean that -4, 2 is a point on the line. And then again, we can check here. So -1, 2, 3, 4, +2. Yep, it's a point on the line. And we can choose another easy number to choose. I could choose t equals 2. R would be negative 1, 4 plus, so if t is 2, 2 times 3, 2. I'll write that in for a change because I haven't been. So 2 times 3, 2. So r is going to be negative 1 plus 6, which is 5, 4 plus 4, which is 8. So therefore the point 5, 8 is on the line. And I don't think we can see that one because I don't have enough room on my graph, but 1, 2, 3, 4, 5, 8 would be a point on the graph as well. So question 2a, state the vector equation of the line passing through these 2 points. Okay, so according to the vector equation of a line, we need to know the position vector of a point on the line, and we need to know the direction of the line. So we're given 2 points, which is great. Okay, so we could use either one of those as a position vector of a point. But to get the direction of the line is going to be the direction of the vector PQ. So PQ, we know is Q minus P. So it's going to be 7 subtract 4 and negative 5 subtract 1. And again, like to reinforce that here. So if we look at these 2 points, 4, 1. Got my markers here. So my point 4, 1, 1, 2, 3, 4, 1 here. That's point P. And point Q is 7, negative 5. So 1, 2, 3, 4, 5, 6, 7, negative 1, 2, 3, 4, 5. So here's my vector PQ. Oops. And if we wanted to start at 0, 0 instead, then we know we would go over 1, 2, 3 and down 1, 2, 3, 4, 5, 6, over 1, 2, 3, 1, 2, 3, 4, 5, 6. And now we have our direction vector. M. So this is vector PQ here, or algebraic vector PQ that starts at the origin at 0, 0. And we got 3, negative 6 on here as well. Now what I want to say, it's interesting about direction vectors, is 3, negative 6 is also the same direction as 1, negative 2. Okay, so that still has the same direction. And all we're worried about with a direction vector is the direction we're going. So we can take a smaller scalar multiple if we choose to, because it's still going to have the same direction. We're not worried about the magnitude of our direction vector, we're worried about its direction. Okay, so knowing that, you can see here without having to draw it out every time. So that's why I didn't immediately say, oops, I need a vector symbol there. I didn't immediately call this the direction vector. The direction vector is going to be my smallest scalar multiple, if one exists, of 3, negative 6. So I see that I can divide each component by 3 and come up with a direction 1, negative 2, which we showed here was still the exact same direction. Okay, 1, negative 2 is still the exact same direction. So there's my direction vector. So my vector equation, R, so I can choose either one of these points to make my position vector of a known point on the line. I'm just going to choose 4, 1 because it came first, no other reason, plus a parameter t times the direction vector. And there is a vector equation of the line. Another vector equation of a line that I know just by looking at this question could have been using the position vector of q, which would be 7, negative 5, plus t, 1, negative 2. Okay? So you may have started thinking about it. So if you look at a line, there's an infinite number of known points along this line, and I could use any one of them to make my OA vector, okay? So there's an infinite number of vector equations of a line. For 2b, it says state the coordinates of 2 other points on the line. 2 other points on the line. So again, once we've got our vector equation, we can just change the value of our parameter. So I could let t equal 1, and if I do that, I'm going to choose this one here. I get r equals 4, 1, plus if t is 1, it would just be plus 1, negative 2, which would give me 5, negative 1. So that would mean 5, negative 1 was a point on the line. And I can let t equal 2. So plus 2 times 1, negative 2. So that's going to be plus 2, negative 4. So 4 plus 2 is 6. 1 plus negative 4 is negative 3. So that means 6, negative 3 is a point on the line. So a line has the vector equation r equals 2, negative 3 plus t times 5, 1. Sketch the line. So this is questions asking, do you understand how to draw a line given its vector equation? So the first thing I would do is I know that this is the position vector of a point on the line. So really when I'm sketching the line, it translates to a point on the line. So I know a point on the line is at 2, negative 3. And I know the direction vector is 5, 1. Okay, this is my x component and my y component. So I know it's parallel to this vector, which means that if I go over to the right 5, 1, 2, 3, 4, 5, and up 1, I should see another point on the line. And reverse that. Left 5 and down 1 should be another point on the line. And then I should have drawn the line there. So there's a picture of this line here. R equals 2, negative 3 plus t, 5, 1. Okay, and that's based on us knowing the direction vector is 5, 1. State 2 other points on the line. So we can just do that by looking here. So this is the one we know. But we had to plot other ones by using our direction vector. So we know, for instance, this point here is 1, 2, 3, 4, 5, 6, 7, negative 2. And this point here is negative 1, 2, 3, negative 4. So our 2 other points on the line. So we didn't have to use letting our parameter be different values. Because we drew the line, we could just take 2 alternate points that we plotted according to the direction vector. So then part C says write another vector equation of this line. So to write another vector equation of the line, I'm just going to choose one of the other points. So I'll choose 7, negative 2 as my position vector of a point that I know, plus t times 5, 1. So it's still going to obviously have to have the same direction vector, just starting at another point. So in this case, here's my position vector of my point on the line, and it's still got the exact same direction. So how many possible vector equations are there for this line? An infinite number, because I can just change that point or the position vector of this point to any point along this line. So there would be an infinite number of vector equations. To find the parametric equations of a line, you begin with the vector equation. And you can think of parametric equations like formulas for the coordinates of a point on a line. So write the parametric equations of this line. So we know that R represents the position vector of any point x, y that's on the line. And what we're going to do to create the parametric vectors is we're going to multiply the t by our direction vector. So we're going to get 3t, 2t. And then we're going to add on the right side. So add the x component, -1 plus 3t, and the y components. And then we're just going to list these. The x value of a point on the line can be found by taking -1 and adding 3t, and then the corresponding y value can be found by taking 4 and adding 2 times t for a certain parameter t. So in two space, parametric equations occur in pairs. And they're, as I said, like you can think of them as formulas to find corresponding x and y values for a given value of t. So those are parametric equations. The parametric equations of the line passing through the known point A, A1, A2 with direction vector M with components M1, M2 are this. So that's just what we did here, where t is the parameter and can be any real number. So we have an example here then. A line passes through these 2 points. Write the vector equation of the line. Okay, so the first thing we're going to do again is find the vector AB so that we can come up with a direction for our line. So 5 minus -2 is 7. 2 minus 3 is -1. Okay, so that's our direction. And there isn't a smaller scalar multiple. So that's going to be our direction vector. So a vector equation of the line, we can choose either one of these points. So I'll just choose the first one, -2, 3, plus our parameter t times our direction vector, 7, -1. Write the parametric equations of the line. So usually just by looking, we can see that to get the x value, we would take -2 and add 7t. And then the corresponding y value would be found by taking 3, and in this case, subtracting t, because t times -1 is -t. So these are our parametric equations. Part C is the point -16,5 on this line. So is a point on the line? Well, for a point to be on the line, we would need to get the same value of t. So if I write these out side by side instead of up and down, if -16,5 is a point on the line, so if x is -16 and y is 5, I should get the same value of t in each of my parametric equations when I solve for t. So in this case, I would add 2 to both sides, divide both sides by 7, and I would get a t value of -2. So when t is -2, I get an x value of -16. Let's see if I also get a y value of 5 when t is -2. So I'm going to subtract 3 here, divide by -1, and indeed I do get the same value of t in each case. So if I do get the same value of t in each case, then I can say therefore -16,5 is on the line. If, say, I got -2 to be t when x was -16, but I got 3 to be t for when y was 5, then I would say no, -16,5 is not on the line. What is the x-intercept of the line? So x-intercepts occur when y equals 0. So again, if I use my parametric equations, I'm going to focus on my y parametric equation because I know they occur when y equals 0. So I'm going to let y equal 0 and solve for the t value. So I'm going to add t to both sides, which gives me a t value of 3. So I know that I'm going to have a point something 0. The y value is going to be 0 when t is 3. So then I come over to my x parametric and sub in a t value of 3. And I get x is 19. So that means my x-intercept is 19, 0. Symmetric equations. Symmetric equations are important because they're the bridge equation. They connect the vector equation of a line to the y equals mx plus b in the standard form from grade 9 to 12 kind of. Okay, so they're a bridge between the vector equation way of looking at a line and the way we've been looking at a line up till now. So to find symmetric equation of a line, it's easiest to start with its parametric equation. So we're going to go back to this line we've been talking about since the beginning. And what we're going to do is we're going to solve each of these parametric equations for t. So I'll write the y1 over here, and we want to get t by itself in each equation. So first, to get t by itself, I'm going to add 1 to both sides. So here, the add 1s would cancel out, so I get x plus 1 equals 3t, and then I'm going to divide both sides by 3. So I get t is x plus 1 over 3. Similarly here, I would first subtract 4 on both sides. So I get y minus 4 is 2t. Divide both sides by 2, and I get t is y minus 4 over 2. But I only consider using my parametric equations for a given value of t. So t is always the same when I'm looking at the x and y parametric. So if t equals this and t also equals that, then these must be equal to each other, and that's our symmetric equation. So our symmetric equation says that x plus 1 over 3 must equal y minus 4 over 2. And you can see that in the symmetric equation, there's no t anymore, okay? No r, it's just in terms of x and y, and could be easily arranged into either y equals mx plus b if we choose, or into standard form, ax plus by plus c if we choose. Also, you can see that in the symmetric equation, you can see the direction vector in the denominator. So the direction vector of the line we knew was 3, 2, okay? We can see also in our parametrics there. So this is our direction vector. So looking at the symmetric equation, you should be able to figure out its vector equation. So its direction vector is 3, 2. We know that a known point on the line is negative 1, 4. So if we go right back to that first drawing here, a known point was negative 1, 4, and our direction vector m was 3, 2. So we can see in the parametric equations, that's where our point is, right here, negative 1, 4, here's our direction. Here's our direction, where's our point? Well, we can see that it's up here, but the signs are opposite, and that's because we did the opposite, like reverse BEDMAS to get t by itself. So you should be able to pick out the point A as negative 1, 4, knowing in the symmetric equations that the signs are opposite because of how we got there. Here we know the point A, in our case, is negative 1, 4, and the direction vector from the parametric equations are the coefficients of t, 3, 2. So notice that the denominator is the direction vector, and you can tell a point on the line from the numerator of the symmetric equation. So the symmetric equation of a line passing through the known point A, A1, A2 with direction vector M, M1, M2 is x minus A1 over M1 equals y minus A2 over M2. But you can only have a symmetric equation if neither direction component is 0, because division by 0 is not allowed. So here's question 5. A symmetric equation of a line is x plus 4 over 2 equals y minus 6 over negative 3. Write parametric equations of the line. So I usually always do the vector equation first because it's easier to get parametric equations from the vector equation for me, okay? So if I'm looking at this, I'm saying, okay, well, I know a point on the line is going to be -4, +6. And I know the direction vector is 2, -3. And that's actually what B is asking. So I'm going to go down here. And I know a vector equation of the line is r equals -4, 6 plus t times 2, -3. And then from the vector equation, I find it's really easy then to write the parametric equations out. So x is going to be -4 plus 2t. And y is going to be 6 minus 3t. Write the equation of the line in standard form. Okay, so to get it into standard form, it's easiest to start with symmetric form. Now remember, standard form looks like this: ax plus by plus c equals 0, where a has to be a positive whole number. So first thing I'm going to do is multiply both sides by the common denominator, but I do want x, the number in front of x, to be positive. So I'm going to multiply both sides by 6. So if I do 6 divided by 2, I get 3 times x plus 4. 6 divided by -3, I get -2 times y minus 6. Then I'm going to distribute, so I get 3x plus 12 equals -2y plus 12. And then I want everything to one side, so I'm going to do 3x, add 2y to both sides, subtract 12 from both sides, so plus 0, which I don't need to show, equals 0. So there's the equation in standard form. So there's my equation in standard form. Question 6, write vector, parametric, and symmetric equations of the line passing through the points r, -6, 2, and s, 4, -2. So vector, parametric, and symmetric. So the first thing I'm going to do is find the vector connecting r and s to see what direction I'm in. So that's going to be 10, -4. So I can divide both of those components by 2 and get a smaller scalar multiple. So I'm going to have my direction vector be 5, -2. All right, so then I've got to write my vector equation. So the vector equation is going to be r equals direction vector of a point on the line. So I'll just choose the first one they give me. Either would be right though, plus t times the direction vector. The parametric equations, parametrics, are going to be x equals -6 plus 5t and y equals 2 minus 2t. And then the symmetric equation of the line, some people can go right to it, and if you can, that's great. Other people need to get t by itself in each of these. They don't see it yet, so I'm going to do that just in case. So if I want t by itself in the x parametric, I would add 6 to both sides. And then divide both sides by 5. So I've got t equals x plus 6 over 5. And then I'm going to do the same thing with the y parametric. So subtract 2 on both sides. And divide both sides by -2. So therefore it would be x plus 6 over 5 equals y minus 2 over -2. That's our symmetric equation right there. Okay? And you can see, how do people just go right to it? Well, they know that, so in my mind I'm going, I have to add 6, so x plus 6 over 5 gives me y. I would have to subtract 2 and then divide by -2. Okay? Other people look at the vector form and they know that it's going to be opposite sign on top, so x plus 6 over 5 and y minus 2 over -2. Direction vectors found in the bottom, points found in the top but opposite. Number 7, find x and y intercepts of this line. So for x and y intercepts, we use parametric form. So I'm going to write out the parametric equations. So we know x equals 5 plus 3t, and y equals 2 minus t. So for the x-intercept, we know that y equals 0. So I'm going to write out my parametric equations side by side. Let y equal 0 and solve for t. So I'd add t to both sides and I get t equals 2. And then I'm going to use t is 2 to see what my x value is. So that's going to be 11. So therefore, x-intercept is 11, 0, because y is 0. For my y-intercept, I set x equal to 0. So I'm going to use my parametrics again. So this time x is 0. I want to solve for t, so I'm going to subtract 5 on both sides and divide by 3, so I get t is negative 5/3. And now I want to find the y value that goes with that, so 2 subtract negative 5/3. I need a common denominator of 3. So I get y is 11/3, which means therefore my y-intercept is going to be 0, 11/3. Do these lines intersect? If so, at what angle do they intersect? Okay, so first of all, I want to just exaggerate this line here, our first line, so it really looks like it's in symmetric form, because that's how we can tell the direction vector. Now this one I'm going to put a little star beside because it looks like it's in symmetric form, but it's not. Okay, so how do we change it so it is? We don't want 1 minus y here. We want y minus 1. So in order to change that, we have to multiply the top and bottom by -1. So it's going to be y minus 1 over -3. Okay, and we'll just kind of show that on the side here. So if I have 1 minus y over 3, if I multiply the top by -1 and the bottom by -1, I'm going to get, so -1 times 1 minus y over -3, distribute the -1, and then I can rewrite that with the y first, so positive y minus 1 over -3. Okay, so all I've changed is what it looks like, because I really multiplied by 1, because I multiplied the top and bottom by the same thing. But now it's in symmetric form because y is first here and positive. So now I can look at the directions. So I should be able to look at this symmetric equation of my first line and right away say that the direction vector of the first line, which I'm going to call M1, is 1, 5. And then again, looking at the second equation, now that I've put it in symmetric form, the direction vector of the second line is 2, -3. So if lines in 2 space are not parallel, okay, so lines in 2 space, basically you've got a x and y axis. The only way 2 lines do not meet is if they're parallel, right? If they have the same direction, then they could never meet. Otherwise, they're going to meet somewhere because the lines go on forever. So these 2 lines do not have the same direction. In other words, they're not, the direction vectors are not scalar multiples. So we could say M2 is not equal to a scalar multiple, so some value of k times the other. So they're not in the same direction. They're not scalar multiples of each other, and they're not in the same direction, so therefore they intersect if we're in 2 dimensions. So that's how we know they intersect. If so, at what angle did they intersect? Well, they intersect at the angle between the direction vectors, because these are the 2 different direction vectors of the line. So we could consider that these Could be tail to tail. I'll do a little not very nice diagram here, but 1, 5, something like that. So there's my M1, 0, 0 to 1, 5, 2, negative 3, maybe over here, and this angle between them is the angle we want to find out. Okay, the angle between the two vectors. So we know how to do that using dot product. So the cosine of the angle between the two lines is going to be the same as the angle between the two direction vectors. So it's going to be M1 dot M2 over the magnitude of vector M1 times the magnitude of vector M2. So it's going to be 1, 5 dotted with 2, negative 3 over the magnitude of this vector, which is going to be the square root of 26, times the magnitude of this vector, which is the square root of 13. Dot is multiply and add, so 2 minus 15 over the square root of 26 times 13. So the cosine of angle theta is going to be negative 13 over the square root of 338, or theta is approximately the cosinverse of that. (135 degrees). It's exact, actually, so I don't need that approximate sign. So the angle between those two lines is 135 degrees. So that's the angle they intersect at. Question 9, state a direction vector of each line. So the line passing through the points C and D. So we can find the direction between C and D by finding vector CD. So 7 minus 3 is 4, 2 minus 4 is negative 2. But I might choose my direction vector to be the smallest scalar multiple without forming a fraction. So I could divide each of these by 2. So 2, negative 1 could be my direction vector. A line that has a slope of negative 4, 5. So we know that slope is, if way back to grade 9, is change in y over change in x. So if I want to convert a slope to a direction vector, the x goes first. So 5, negative 4 is my direction vector. And if you think about this again, the slope of, so down from 0, 0, down 4 over 5. So from 0, 0, we go down 1, 2, 3, 4, and over to 5 is also a direction vector of 5, negative 4. A vertical line passing through the point negative 6, 5. So here's our point, negative 6, 5. If it's vertical, what's its direction? So you could think about it being parallel to the vector starting at 0, 0 and going upwards or going downwards. So the simplest form would be if this point here was 0, 1. So the vector from 0, 0, the origin, to 0, 1 would just be the vector 0, 1. It's kind of the simplest vertical line direction that you could present. A horizontal line, so in this case we're going to have a line that's going horizontally. Simplest direction vector we could give for that would be parallel to the direction 1, 0, which is this direction here, from 0, 0 to 1, 0. A line parallel to this line, so parallel means same slope as or same direction as, so parallel means same direction. So in our case, our direction, if it's going to be parallel to this line, it's going to have the same direction. We know the direction vector is 4, 1, so it's going to have the direction vector 4, 1. Perpendicular to the line, another very important concept in this unit. So perpendicular to the line. So we know from grade 9 that if we knew the slope, the perpendicular was negative reciprocal. So similar idea here. If our direction vector is 1, 4, so that would mean 1, 4, if our 1, 4 was our direction vector and we wanted to convert that to a slope, the slope would be, oh, sorry, my direction vector is 4, 1. My direction vector is 4, 1, so that's going to be over 4, up 1. So that's the vector from 0, 0 to 4, 1. So that means over 4 and up 1. So that means our slope would be 1/4. So we know from grade 9 that if we want a perpendicular slope, perpendicular we could call it, a perpendicular slope, as our little perpendicular symbol there, it's going to be negative 4 over 1. And then if we want to write that as a direction vector, remember slope is change in y over change in x. So as a direction vector, it's going to be 1, negative 4. And you can see how these are related to each other. So if we want to be perpendicular to the direction 4, 1, you're going to flip the components to 1, 4 and make one of them the opposite sign. So if they're both positive, one of them has to be negative here. If one of them's negative, then they'd both have to be positive. It's analogous to a negative reciprocal. Okay, we have a few questions left to do, but I don't think we'll have enough time on this video, so I'm going to stop and then I'm going to finish on the last 2 questions on the next portion here.